Can you hear me? Good morning, everybody. Can you hear me?
Yes. Can you hear me?
Very good. Thank you very much. Yes, I can hear you. So finally, we are about to start. So I'm very sorry about this terrible delay, but it was because of technical issues with the local internet connection. But at last, I'm happy to welcome you at the 25th International Conference on Computational Science and its Applications, and our workshop on scientific computing infrastructure. Yes, and we are happy to start. And the first talk will be presented by Anton Arja. Anton, could you please share your screen, and you are welcome to start when you are ready. Anton, can you hear us? Anton, good morning. Can you hear us? I don't think we can hear you. No. Okay, Anton says he cannot hear us, but it looks like we should have proper connection. Maybe we can try to switch the talks then. Maybe Anna is ready to start. Are you? Yes? Do I have your slides? You sent me.
Excuse me?
Hello, yes. Can you hear us?
Yeah, of course. May I present first?
Would you like to present first?
Yeah.
And your talk is, could you please give me the program? So is your talk the last one in the section?
Our presentation is the last presentation.
Yes.
Monha, Yuna Shishkina, and Swan Kian Nguyen.
I think we can do it, Anna. So let's launch this one, or you would like to be the first? Yeah. Никак. But would you mind waiting for your turn then? So we will try to start the second presentation now, and then you will get your turn later on. Is it okay with you?
Okay, it's okay.
Okay. So I would still invite Anna, but Anton, can you check your voice again? Maybe you can say something and we can hear you, because it seems that the others have proper connection. Yuri, we can hear you, Yuri. So let's go on with Anna's talk now, and then we will see our schedule, because we have some issues with Anton's presentation. So we will try to stick to the order which is in the program. What is the share button? I'm not sure where I can share my screen. Is it this one? Maybe this one. Which one? I think I would like. Okay, I believe you should be able to see the slides now. So I would like to welcome Professor Anna Golovkina with her talk on neural ordinary differential equations based on TM solver to predict time series data. Welcome.
Thank you once again. I will start. I try not to take much of your time, so that not to fit out of the schedule. Yes. So First of all, I would like to start with a short agenda of my presentation. I want to highlight the challenge that was taken as the motivation for this research. A bit brief review of modern solutions, their bottleneck, the core idea of the proposed method, and we go through experiments and results and some conclusions. So the challenge was well known. It's modeling time series data, especially if this time series related to some physics-based process. It's a critical topic in many fields, and traditional models like autoregressive models or recurrent neural networks, they impose rigid and discrete time structures. And sometimes this leads to challenges with irregularly sampled data. When observations are not with fixed time intervals, we need to invent some hints how to regularize them. And also some problems related to continuous problems when we want to capture underlying dynamics of the system that involve continuously. So to address these challenges, in 2018 was proposed a model narrow ordinary differential equations at NIPS conference. It's use continuous time differential equations departing from the discrete layers. So the core concept is the derivative of a hidden state is parameterized by a neural network. And here, the right side of differential equations is a neural network with the parameters that we try to learn is theta. So the advantage of this concept is we naturally handle variable time intervals and irregular data with this representation and learn smooth trajectories and can have lower memory cost during training via a joint method. But the performance of this model is strongly influenced by the choice of the numerical solver that is used for integrating these differential equations lying behind the model. And most often, some conventional solvers are used, like Runge-Kutta, Dorn-Prince 5. And sometimes we face with the computational costs that it may require large number of functions evaluations that can slow down training. There can be some stability issues related to stiff or complex dynamics that these solvers can handle with. And higher precision usually can come with a significant computational costs also. And we decided to propose to use another type of solver for such models is tailor mapping solver. It's numerical integrator that leverages polynomial approximations of ODE solutions. So by this representation, we basically get the general solution of ordinary differential equations, and these matrices of the solutions, they does not depend on the initial conditions. So basically, we don't need to recompute the scheme when our starting point changes. Also, we can have kind of explainability of this solution because we understand explicitly with what strengths we depends on what parameter, and also we can simpler compute gradients and also can avoid some memory backpropagation issues with these solver steps. So what we proposed to do to make a hybrid architecture that was inspired by one of narrow ODE models when it was combined with a traditional recurrent neural network. So the components are narrow ODE core. It's the main network that defines the dynamics of the system, and hybrid solver that we choose in what situation is better for us to use the team solver or dormant print solver. And the decision what solver is the best for us is taken by a classifier that is based on multi-layer perceptron for the particular time window. And we tested the proposed concept against several other narrow ODE variations in two scenarios. First one was univariate time series prediction with synthetic data and real-world data. It's humidity index from the open source data from Kaggle competition resource. And another example was a real data set that was collected at our test bed at St. Petersburg University. It's a vibration facility that is used to model different types of defects that can appear in rotating machines and so on. So the main challenges was to understand what kind of defect we are facing right now, according to the vibration signal that we can collect from this test bed. So we collected vibration signal in 3 perpendicular directions in 4 points that are indicated on this picture. And also we imitated different kind of defects that can happen with rotating machines by, for example, putting some weight on the rotating wheel. And based on the weight heavily, this disbalance was more explicit or less explicit. And another kind of defect was the weakening of the supporting structure between second and third bearing. So we just screw out some of the facilities so to disbalance the systems. And also the ideal data set was where we didn't have any type of defects. So for univariate tasks, the best of models for narrow ODE was augmented neural network. It demonstrated the highest accuracy and also, but the train time was not the best one. Maybe it was attributed by its ability to learn richer dynamics in larger state spaces. The proposed model showed the competitive performance. It was not the best one, but still it outperformed the classical, the baseline. The narrow ODE was what was originally proposed on this data set. And for multivariate vibration data, the best one was Hamiltonian neural networks. And maybe it can be explained because with this neural network, we try to preserve Hamiltonian of the system. And as vibration system is a mechanical one, that it can be a good choice to model it with a system like that. The proposed model achieved the second best accuracy and also provide effectiveness and was running faster than other alternatives aside Hamiltonian neural network. And also a side result that we got from these models is that based on the form of the signal that we collect from the vibration stand, we basically can differentiate between them, and you can see that without defects, the shape of this Tor, I would call it, it's different when we introduce some kind of deviations from the perfect condition. And when we screw up some fixing mechanism, you see that the vibration goes crazy. And that also put us to the idea to use the prediction model as the method of classifying the type of defects we can face in the real world data. And here you can see the difference between the ideal data and generated with the predicting model. And you can see that based on this form of this deviation, we already can make a conclusion that is not a normal condition. So the prediction model was learned with the data without defects, and then we used it to predict on the data with defects. And based on the difference between the predictions and the original defective signal, we can also realize what exact type of defects we are facing with. Yeah, so thank you for your attention.
So, does anybody have a question? So please ask. I also encourage our online audience to ask questions. Okay, I have a small question first. So we use neural networks as the main mechanism, and you have to teach the neural network. So how long is it? So how much effort do you use to train the networks? Can you compare it to traditional methods? Okay, this is the train time.
Yes. It's not so long, I would say. Even for the longest one is a minute and a half, I would say.
But you have to teach it on already labeled data, right? So you have to know.
No. It's not a classification network. It's a prediction network. So we just predict the future values, and then based on the deviation of these predicted values with the signal that we in fact have, we can then make a conclusion that it's not good.
So it always predicts the correct behavior.
Yes, it's always been, yes.
In fact, it's not that what's predicted.
Based on the difference, we can understand that something goes wrong.
Because I understood you also said you can classify the errors, right?
Yes, but you can see that we visually can differentiate between different defects, but it should be another kind of model if we want to do this automatically.
Okay, so now you just see it, it's different, and you can classify it with your own eyes.
Yes, like with these also models. We see it with the eyes, but in future we are going to make the models that can differentiate between them automatically.
Go back to these comparisons. Yes, table. So all these ones are based on neural networks, right? Augmented ODE also.
They all based on narrow ODE. Yes.
But if you compare to more traditional ways of predictions, like classical machine learning, can you say any, what's the difference?
The difference is that these kind of models not so reliable in terms of long-term predictions. So if we see the classical one, so if we will see the deviations with the predictions of this model and the signal, it can be because the model goes bad. Usually it happens like that, the degradation of it. But here the model catches the physics underlying the process, and if the deviations occurs, then it's the signal that physics became different. So it's the reason of the defect. Yes.
These models are better in case they predicted more precisely, and
more reliable.
If you get the error, then it's probably indeed the defect, but not the problem of the model.
Yes.
Any more questions?
Very quick question. How many people?
Yeah, you mean input signals? So it was in this case it was 3. In this case it was 1. Oh, unfortunately, we didn't try this, but it's a good idea to test. I would say, but here when we have a one parameter only to predict, it's quite straightforward. But here, when we have three parameters, multivariate prediction, we also consider that these signals are interconnected to each other. So they are connected with this differential equation system, actually. And if one parameter is missing, I guess that you mean in the inference or in the in the inference, I guess. I think that there might be a problem with the predictions. So, but we didn't try, but I think that it can not good give good result, unfortunately. Yes.
Thank you, Nadia. Let's continue with our next talk. So let's try to switch back to Anton's talk, who is scheduled the first one. Anton, can you hear us now?
Yes, can you hear me?
Very good. Yes, we can hear you. Could you please share your screen?
Yes, of course.
Yes, we can see you.
Can you see my screen now?
Yes. I need. Yeah, I think it's clear enough. Yes, very good. Thank you. So you can start, please.
Okay. So good morning, everyone. My name is Anton Arja. I'm a student at St. Petersburg State University, and today I would like to present our work an autoencoder and kernel density estimation-based approach for time series anomaly detection. This is a fully unsupervised method for univariate time series anomaly detection, and I will walk you through its core ideas, design choices, and evaluation results. Time series anomaly detection is a fundamental task across domains like industry, medicine, finance, and many others. However, despite the amount of work done in this field, there is no single method that can be called a universal leader. Performance often depends on the dataset and anomaly types. On top of that, manual labeling of real-world time series is usually an impossible task, either because of scale or because ground truth is simply unavailable. So unsupervised methods are of great interest. With this motivation, we propose a method that combines autoencoders and kernel density estimation for time series anomaly detection, and method is called KDAE. The idea behind KDAE is simple but effective. We break time series into non-overlapping segments. Then we use an autoencoder to encode each window into a lower dimensional vector. Next, we apply kernel density estimation to estimate windows density. And finally, we convert these density values into anomaly scores. The key assumption is that anomalous patterns are less frequent, so they should have a lower density in the latent space. Just a quick recap, an autoencoder is a type of neural network that is trained to perform nonlinear data compression in unsupervised mode. A variety of architectures can be used to build an autoencoder, but in our case, we use a one-dimensional convolutional autoencoder, which is efficient for time series. Kernel density estimation is a non-parametric method for estimating probability density function of a dataset. We use a Gaussian kernel and compute densities in autoencoder's latent space. These two tools, autoencoder for compression and kernel density estimation for density form the core of our anomaly scoring. Our autoencoder uses 3 convolutional layers in the encoder, followed by a linear projection into 4-dimensional latent space. The decoder mirrors this structure using transposed convolutions. We fix the input window size to be 23, which allows us to avoid zero padding and maintain consistent tensor shapes. Also, we train our model on the whole dataset and not just normal data. So the method works without any prior knowledge of what's normal or anomalous. Unlike many other approaches, we use non-overlapping segments of time series, which significantly reduces computational cost. Now, how do we go from encodings to anomaly scores? First, we need to choose the kernel density bandwidth, which is crucial. We propose a data-driven way to choose it using a quantile-based heuristic. We find the so-called middle point, which is the encoding closest to medians of all dimensions in latent space, and then we compute distances from all data points to the middle one. Next, we choose a quantile Q of these distances as a kernel density bandwidth. After computing kernel density values, we do Z normalization and then apply a sigmoid, which draw values into the unit interval. And finally, we set anomaly score of each time series point equal to the score of the corresponding segment, which is reasonable if anomalies are long enough. We tested KDAE using the time eval framework on Gutentag dataset, which is a collection of synthetic time series with various anomaly types and patterns. We use 3 metrics for evaluation, which are ROC area, PR area, and average runtime per point. We also compared our method with 25 other unsupervised algorithms evaluated by other authors on the very same data. We conducted experiments to choose the number of training epochs and best bandwidth parameter. We found that 2,200 epochs offer a good trade-off between performance and overfitting. And for kernel density bandwidth, a quantile value of 1,000th gave the best ROC area score on average. These plots shows how ROC and PR areas respond to these parameters. KDAE performs quite well compared with other methods. It outperforms 40% of algorithms by ROC area, 60% of algorithms by PR area, and 60% by runtime. Only one method outperforms KDAE across all 3 metrics, and most high-performing models are heavy computationally. So KDAE offers a balance of quality and efficiency. We also analyzed how KDAE performs for different types of anomalies and base signals. The best results were for frequency, extremum, and variance anomalies, and the weakest performance was for platform-type anomalies, because for that type of anomalies, they tend to produce many similar encodings, which goes against our base assumption of low density of anomalies. Also, the methods work best on periodic signals, which is a common trait of many anomaly detectors. Here we show visual examples of how KDAE performs on various time series. For example, you can see how it does well on ECG type signal or sign-based signal. For non-periodic signals, it also can discover anomalies, for example, as in that picture, but in that case, we have more false positives. And the last example is an example how model fails to discover platform type anomalies because of the reason I stated before. This highlights strengths and limitations of the method. To conclude, we introduced KDAE, an unsupervised algorithm that combines autoencoders and kernel density estimation to detect anomalies in time series. It performs competitively with the state-of-the-art methods while being computationally efficient and easy to apply without prior knowledge about data. Their directions for future work could be the improvement of the process of bandwidth selection and adapting the model to multivariate time series. Thank you very much for your attention.
Thank you, Anton. So please, questions from the audience? Any question? Could you please come here? Maybe it's not enough.
Anton, good morning. And how do you see the future of your work? The next step.
As I said, the very important step is adapting model to multivariate time series. They are observed very frequently, but the architecture of the model should grow as the dimensionality of time series increases. So I think it would be great to adapt the model to multivariate time series.
Thank you.
I also have a question. So you said that your algorithm is not traditional in the sense that you work with detecting anomalies in lengths, at lengths, like the whole time series, but not particular anomaly points. And my question is that now you detect if there is anomaly or there is no anomaly, right? In the time series. So the question is, can you classify them later? So what kind of anomaly you see?
No, the model can do it. For each point of time series, the algorithm shows a number from 0 to 1, where 0 is absolutely not anomaly and 1 is definitely anomaly. But it does not classify them. It just decides if it's anomaly or not, depending on the density in encoders latent space.
Yeah, so my question is, do you think it is possible to extend your method to be able to classify them also? So the example could be that you work with the electrical meters data, and what do you want to see and what do you want to find in this kind of data? If there is someone who is cheating, so he can be doing what? He can be stealing energy, one type of anomaly. He can be using illegal mining hardware. It's another type of anomaly. So this kind of also lengthy anomalies, I wonder if the method could be extended to also provide this kind of estimations. What is actually happening there?
It sounds more like a task for supervised learning algorithms. When we have a labeled data set and we can train our model to classify exactly what we want. But since this method is unsupervised, it is hard to take from him our classes of anomaly.
But can this method provide the information which can be fed to another supervised method that could help identify this?
Maybe. I think yes.
Yeah. Okay. Do we have more questions? No? No? Online questions, maybe? Okay, no questions from online. Anton, thank you again.
Thank you.
And let's proceed to the next talk. And next talk will be from Yuri Matyushin. Yuri, could you please share your screen.
Okay, sure. Okay, I hope you can see my screen now.
Yes. Yes, we can see it full screen. Yes.
Okay, so hello dear colleagues. Today I would like to present our work on MLE RBA, or a machine learning powered risk-based authentication algorithm, which we're developing at this point. So I would like to begin by explaining the motivation behind RBA and the motivation behind developing a new RBA algorithm. So at the moment, the most common way to confirm a user's identity is password protection. So it is, of course, a very simple and very well-known method, but it also has its weaknesses. So, for instance, passwords can be weak, they can be reused, and they can be vulnerable to a number of attacks, such as phishing, dictionary attacks, and so on. And because statistically a majority of data leaks involves weak or strong credentials, it is essential to develop more robust, more secure authentication methods. One way to approach this is by using multi-factor authentication, which is to say, to require the users to go through additional steps to confirm their identity. So this improves security but can hurt usability, which, in other words, it can be less convenient for the end user. Another approach is risk-based authentication. So what RBA, or risk-based authentication, does is that it computes a risk score for each login. So it tries to determine the probability that it tries to compute a probability that login attempt is an attack, and it only uses. I'm sorry, can you hear me? I'm sorry, can you hear my presentation right now?
Yes, Yuri, we can hear your presentation, but I think Evelyn has not muted. I will try to mute her. Evelyn, could you please mute your microphone? Yes, thank you.
Okay, so I'll continue now. So yes, basically RBA determines the risk score, the probability that the authentication attempt is an attack attempt, and it only uses multi-factor authentication if the risk score is sufficiently high. So this approach is currently gaining popularity, and it's used by such major players as Google, Facebook, LinkedIn, and so on. So to explain how it works in more detail, it analyzes a number of contextual signals. So the IP address, the user location, the device parameters, and so on. And it tries to check whether each of those factors matches the existing user profile. So for instance, if the user always connected from the same country and then suddenly connects from another country or from another device or operating system, these kinds of mismatches can raise the risk score. And if there are enough mismatches and the risk score exceeds a certain threshold, then the system raises a flag and it requires some additional steps to further verify the user's identity. So the advantages of this approach is that it runs in the background, so legitimate users will most likely not have to go through any additional steps, and it can also learn from past behavior as it builds more accurate user profiles. The specific RBA approach that we're basing our algorithm on was developed by David Freeman and colleagues in 2016. So the reason why we chose this approach in particular is, well, first, it's something of a foundational study in RBA, where several other studies are based on this approach, and also because it's publicly available, unlike the RBA approaches of Google, Amazon, and other major companies, which are usually black box algorithms. So to explain very briefly how it works, it is a naive-based algorithm which computes a risk score based on a likelihood ratio. So it uses a number of contextual features and determines how likely these features are for any user in the case of an attack versus how likely they are in the case of a legitimate user. And if the ratio exceeds a certain threshold, then it requires additional verification. So it uses user-specific frequencies, so which means that if a user connects, for instance, with a certain IP or a certain device a lot, then the likelihood is high. It also assumes that all features are independent of one another, which is what makes it a naive Bayes classifier. And it also incorporates global reputations. So for instance, if an IP address is associated with past attacks, then it raises the risk score. And finally, in case if it doesn't have any information about a certain feature, so for instance, if a user connects from a new city, it can use smoothing or backoff. So inside of a city, it uses information about a country or a region. So this approach has several limitations. So for instance, every feature is treated as equally important by default, unless you manually change the weights. And the threshold is also set manually and does not change or adapt. And it also does not use any temporal or aggregate history features, which might improve threat detection. So in some scenarios, it can yield higher false positives or false negatives. So our approach, Emily RBA, is based on Freeman's idea, but it also incorporates several machine learning techniques to automate feature weighting and thresholding. In particular, we use anomaly detectors, light GPM classifier, and adaptive threshold tuning based on RSC curve analysis. We have implemented this approach. We have trained and tested it on an open source logic dataset, and we have compared it against 2 other RBA algorithms. So on this slide, you can see the overall architecture of our approach. The next several slides will explain each part in more detail. So as you can see, first we have basically feature engineering. We use several contextual features. We create our own feature, time-series/login. We use target encoding for categorical features, and we also use resampling to make the training set more balanced. Then the balanced training set is used as an input for anomaly detection, which consists of 2 different detectors. Their combined anomaly score is fed to the classifier, light GPM model, which in turn outputs a risk score. And finally, the system chooses a risk threshold based on basically balancing security and usability. And by comparing a risk score for each login with the risk threshold, it decides whether to allow an extra attempt to connect to the system or to require additional verification. Okay, so the first step is, as I said, feature engineering. We use, as you can see, a variety of features, which we believe can make it harder for an attacker to fully fake being a legitimate user. We also add our own temporal feature, which is time-series/login, which can help detect unusually fast or slow login attempts. And we also use target encoding on categorical fields such as country. So currently, using the average number of attacks associated with each feature. So for instance, if connecting from the US or say Canada leads to an attack in 5% of instances, we can replace this country name with 0.05. So the model learns which categories are riskier. So this basically is a variation of Freeman's algorithm reputation score. And we also process any missing values. The next step is resampling, because login data can be imbalanced. So for instance, legitimate logins can outnumber attacks, which can lead to bias in training. We apply a technique called smooth DOMEC, which consists of 2 parts. Smooth or synthetic minority oversampling technique is a technique to basically create artificial additional data points in the minority class. And atomic links, basically atomic link means 2 data points that are each other's closest neighbor, yet they are members of 2 different classes. So in our case, we remove the member of the majority class in each atomic link. So what this achieves is that the training set is more balanced and there is a clear distinction between legitimate logins and attacks. So we use this balanced training set for anomaly detectors and for the classifier. So the next step is anomaly detection. We use a combination of two approaches. The first is local outlier factor, which measures how each point, so each login attempt, is isolated from its nearest neighbors. So the high LAF score means that a login attempt is unusual compared to other similar attempts. And isolation forest is more of a global anomaly detectors. It is a tree-based method that isolates the combination of features that are unusual across all login attempts. So the anomaly scores are combined by the formula you can see here. And what I would like to note is that these anomaly scores do not directly contribute to the risk score. So they do not say that this login attempt is risky, they just say that it's unusual and give this information to the classifier. So for a classifier, we used LightGBM, so it's a gradient boosted decision tree ensemble. And the reason we chose it is that because of its high training speed and efficiency, also improved accuracy compared to, for instance, random forest, and also because it is compatible with large complex data sets and high feature spaces, well, which fits our use case. We also apply probability calibration so that the model's output can be accurately interpreted as a risk probability. So it finally outputs a score between 0 and 1, which represents the estimated probability of the login attempt being an attack. So of course, 0 means that it's definitely legitimate, and 1 means it's definitely an attack. So as for the data set, we use an open source data set of login attempts collected by the Data and Application Security Group. So it is based on data from a large-scale online service, which collects data of more than 33 million login attempts and more than 3.3 million users. So it was collected over a year. So I'd like to note that because the original data included some sensitive information, such as IP addresses, this data set is, well, not exactly real life, but it's based on the collected original data. So it's very close to real. And it includes a number of features which we use, such as user IDs, timestamps, network information, device and client data, and also authentication outcome. So whether logins succeeded or failed, and whether there were an attack or not. So for testing, we split this data set into train and test categories, and we also use two other algorithms as baselines. The first is the implementation of Freeman's algorithm, which I discussed earlier, and another is so-called simple heuristic from another article. So this is the basically simplest possible approach to RBA, where risk score only depends on the number of feature mismatches. So number of features that we do not see even once in the user's login history. And for evaluation metrics, we use AUC RSC, equal error rate, and confusion matrices. So these are the testing results for the simple heuristic. It's the equal error rate is about 31%, well, exactly actually, and AUC RSC is about 0.69. Next is Freeman's algorithm. So equal error rate is lower, about 24%, and AUC RSC is 0.76, so it's of course more accurate. And our algorithm has achieved equal error rate of less than 20% and AUC RSC of about 0.87. So to discuss these results, we can see that our algorithm demonstrates improved performance compared to both original Freeman's algorithm and the simple heuristic. However, we found that it still shows a relatively high error rate, especially compared to the more traditional authentication algorithms. So based on this, we believe that risk-based authentication should not be relied upon as a single way to confirm a user's identity. Instead, it should be used as a part of a hybrid authentication system, which incorporates several several different approaches. So, and also there is a possibility of further improving our method by conducting experiments with a variety of machine learning models and classifiers, and also if we gain access to more varied data sets. And final thing I want to discuss briefly is one possible future work direction, which is to say the integration of our system into a continuous authentication framework. So, for instance, as I said, RBA works best as a part of a hybrid algorithm, and the second part of this algorithm can be dynamic keystroke recognition, which identifies the users and authenticates the user by the way they basically use a keyboard, the way they type. So this kind of hybrid approach can be both secure, it can determine the user's, it can authenticate the user not only at the point of beginning of the session, but also throughout the session. And at the same time, it remains unobtrusive, so the user does not usually have to go through any additional steps. He can continue working with the system without any problems, as long as the user is legitimate and as long as the system does not recognize the user as a potential threat. So that's all I wanted to say today. Thank you for your attention.
Thank you, Yuri. Please, questions from the audience? I have a small question, Yuri.
Yeah.
You mentioned that one of significant feature of the methods, at least Freeman's method, is the IP address.
Yes.
And now a lot of people use VPNs, and both legitimate users, like I use VPN for my own purpose, and I just forget to turn it off. And immediately, in next minute, I connect with completely another IP address.
Yes.
Or on the other hand, malicious users can also use VPNs to pretend that they are from like USA or some good countries, so to say good, instead of their risky countries. So how do these methods work with these situations, and how is your improved method tackles with this problem? Yes.
So, yes, it is a known problem in RBA. So it does increase risk score if the user connects from an unfamiliar IP, like for instance through VPN. So for this reason, the risk-based authentication collects not only IP addresses but a variety of different factors. So location, device, operating system. So yeah, and in our approach in particular, we also use some additional features.
15 after 11.
Okay.
Yeah, additional features.
Yes, Yuri, please go on.
Yes. So yes, basically we use not only IP but a number of features. We create our own features like time since last login. So we build more comprehensive picture of the user. So the different IP can raise a risk score, but it is also balanced by all the other factors. So, and of course, because our system is trained over time, it can learn that different IPs do not necessarily correspond to an attack attempt, so they can be less important and can decrease their weights. So, as compared to more earlier algorithms in which all weights are fixed.
Thank you. Do we have more questions? No questions. Okay, Yuri, thank you. And let's continue with the next talk by Evelyn Hakizimana. Evelyn, could you please share your screen? And in total, we have 30 minutes, or at least even a bit less. So let's try to hurry up. But use your time. Yes, Evelyn, we can see you.
Thank you.
Yes, we can hear you, but we don't see your screen yet.
1 minute, please.
Okay. Yes, we see it now.
Thank you. Can you hear me?
Yes, we can hear you very well.
All right. Thank you very much. My name is Evelyn Hakizimana. I'm a PhD student at the University St. Petersburg State University. Machine learning, artificial intelligence, and machine learning as a faculty or department. Here, my topic is the real-time IoT data security. Here, we will start with the problem statement of our project. The IoT, the rise of IoT devices has introduced significant vulnerabilities, especially when these devices lack proper security configurations. And one of the most pressing threats in the distributed denial of services or DDoS attacks, which exploit these weaknesses to flood networks and disrupt services as etc. And the traditional detection systems often fails to detect such attacks. I mean, these denial of services or DDoS in real time, especially in regions like Africa where the infrastructure may be limited or varied. So our problem, therefore, is not only the increasing frequency, but and also complexity of the distributed denial of services attacks, but also the lack of the real-time detection models that are suitable for the IoT environments. As the objective of the studies, our main goal of this study is to improve real-time distributed denial of services detection in IoT environments using hybrid machine learning approach. Specifically, we aim to analyze this nature of the DDoS attacks and understand why IoT devices are especially vulnerable. The second is to evaluate existing detection techniques, particularly within the African context. The third one is to develop a new detection framework combining LSTM and ART algorithm to improve accuracy and adaptability. And the fourth one is the assess the systems using standard metrics such as F1 score, precision, and recall. The three metrics will be used to ensure the performance and reliability. As the methodology we used is involving the designing of hybrid detection framework that integrates to the two types of machine learning algorithms, which are the LSTM as the long short-term memory LSTM and adaptive resonance ART. The LSTM is actually excellent at understanding time-based patterns, which is useful for detecting suspicious changes in traffic flows over time. And the ART, on the other hand, is good for adaptive classification. It can learn new attack types without forgetting older ones. So together, these two algorithms help us to detect both known and unknown DDoS attacks effectively. Here we also start by collecting live network traffic data from IoT devices and gateways. This data is then processing. Sorry. This data is data from the LSTM is processed from the unknown or known from the known or unknown data collected by the ART algorithm. So, and the output is then passed into the art module, which clusters and refine those productions, allowing us to recognize new or evolving attacks without retraining the models. A detection workflow and evaluation. Here I can show this. Sorry. One minute, please. I can show here I'm sorry, I was not able to put in there. So detection is the entire the pipeline of our project. So detection process is several key steps. For the first step is we continuously to collect data and a real-time detection, and we continue to collect data and the traffic data from the real-time sessions. So those data are being collected in the IoT environment, and data collection systems begins to continuously collecting network traffic data from the IoT devices and the associate gateways. So this forms the raw input for the detection pipeline. And here the second is we apply the preprocessing to clean and prepare the data. Preprocessing is the data undergoes and several preprocessing steps to enhance equality and capability. Here we have some, you can see the sub processions, which is validations and noise reduction and normalizations. So here the process of normalization is to get the feature consistency and feature encoding to prepare the data for the sequential analysis. And validation is to filter or to filter out on irrelevant data or corrupted data. So the third one is the pre-processed time series data is sent to the LSTM model. As you can see here, so it's sent to LSTM model, which identifies temporal patterns and produced probabilities of different behaviors. So the LSTM analysis after preprocessing the data is segmented into the into time series as we're dealing with the real-time data, and these time series windows and pass through the through the LSTM learns temporal dependencies in traffic behaviors and performs preliminaries classifications. And here the second step will be these probabilities are passed into the art, our art algorithm. So after passing through the model, which groups similar outputs and improves uncertain or ambiguous predictions. So here the LSTM produces probability distributions over possible traffic classes using the softmax activation function, which we have it in the machine learning. So this is also indicates the likelihood of the different types of behaviors like DDoS, which we are dealing with, and DOS, or maybe other types of attacks like Mirai, but here we are focusing only on the DDoS, distributed denial of services. Finally, a decision module determines whether the traffic is normal or an attack. Because we are dealing with the DDoS here, it will be detecting only a DDoS, but it will be showing also another types of attacks, but we will be focusing only the DDoS attack. So this system is designed to function in real time, adapt to change attack strategies, and ensure high accuracy while minimizing false positives. And the art algorithm clustering and the clusters and the LSTM combined together, with which gave us the solutions or the results of the high accuracy. So let's proceed on our PowerPoint, please. Here, I will show the key findings. As the results of that process is this is the results of the LSTM model accuracy. The LSTM model accuracy, which gave us the high results, like the high accuracy. So this model accuracy steadily increases with the training, reaching a peak of as you can see on the graph is about 98%, and this accuracy shows the LSTM network is capable of learning temporary relationships in network traffic and differentiating between the DDoS attack or the normal patterns, or DDoS attack or normal patterns. Normal patterns means not attack. And here it is the LSTM modelers, and it is constant convergence of the accuracy measure demonstrates the model ability to generalize effective to unknown data, which is critical for the real-time detection in dynamic IoT context. And the LSTM power to recover sequential patterns, and this will be enabling to be detected by the tiny anomalies indicative of DDoS attack. And here we have the classification report and metrics. The classification report here, our LSTM model provides the exceptional accuracy and in the 3 identification with the flawless precision, recall, and F1 score, which is 1, as I mentioned here with the purple color. The DDoS attack, it shows the recall is 1, F1 score is also 1, and the precision is 1. Here will be the ART clusters on the LSTM software outputs. So they are our ART performs real-time clustering of the probability result generated by the softmax layer of the LSTM. By grouping these similar softmax distributions, this algorithm can be dynamically refine classifications and identify new or evolving attack patterns without retaining. So this real-time clustering significantly improved the adaptability and responsiveness to improve the adaptability and the changing of the model in rapidly changing in IoT environments. As conclusion, in conclusion, our study demonstrated that the combining LSTM and ART in a hybrid framework, I'm saying that it's hybrid because we combine 2 algorithms. So this hybrid framework offers a powerful real-time solution for detecting DDoS attacks in IoT networks. So we achieved about 98% accuracy with strong performance and across all the evaluation metrics. So the model is also proved capable of adapting a new threats without constant retaining. And some key lessons learned is the importance of preprocessing of accurate time series analysis, and this is how the hybrid models can outperform single algorithm. In dynamic environment, we also saw the arts as learning greatly enhances the system is the resilience to unknown attack. So for the future work, we plan to expand the models used across other IoT platforms like smart cities or industries or tech firms. And the second one is the integration of automatic response systems for real-time mitigation and optimizes the model of the run efficiently on lightweight edge devices. And finally, enhance it in robustness against the adversarial attacks. In general, this research provides a strong foundation for securing IoT infrastructures and shows how advanced machine learning can be tailored to meet modern cybersecurity challenges. Thank you very much. Thank you for your attention. You are welcome for if you have some questions, and I'll be here to answer. Thank you very much.
Thank you, Evelyn. Please, questions from the audience? I have a small question. So you said you use art for classification, right?
Yes, please.
And it works with labeled data, so you can classify this labeled attacks. But you also said that the method allows to detect something which is not known. Is it correct?
Yes, please.
So how does it work? So how does it classify the new threat? So it does not know it yet, but he can detect that it is a threat. So can you say a few words about this?
Yes, please. Thank you for the questions. First of all, our system, the only target was to detect the DDoS, distributed denial of service. But as we know, like in IoT devices, we have many attacks. We can face many attacks, which are it can be mirrored, botnet, DOS, and others. But here, as I showed here, I'm sorry. Can you see my screen, please?
Yes.
Yeah, as you can see here, those are the attacks that our system collected or identified. But because our project is only to deal with the DDoS attack, that's why I highlighted the DDoS attack. So this system will be able also to identify maybe the dictionary brute force, the mirror, the reconnaissance. But if the new attack, because we are dealing also with the real time, if the new attack occur, the system will be also to show, we will be able to detect. And I mentioned only DDoS because that was we were saying, but as the results here, you can see it shows many attacks.
Okay, thank you. Thank you.
Thank you.
Do we have more questions? No. Okay, thank you, Evelyn. Thank you again.
Thank you very much.
Let's proceed to our next talk. I might be mistaken in pronouncing your name. I'm sorry, but Xuan Han Nguyen?
Yeah.
Is it
Okay.
close?
Yes.
Yes.
Okay.
You can say your name, please, yourself.
Okay, my name is Xuân Hiên Nguyen, and I'm from Hanoi University of Industry. Let me share my screen.
Yes, we can see your screen.
Okay. So, good morning, everyone, again. My name is Xuân Hiên Nguyen from Hanoi University of Industry, and today I'm delighted to present our research title, Extending the Solstice Path Algorithm for Large Graph with Circles, a Parallel Computing Approach. And this is a collaborative effort with Monha from Telecommunication University of Vietnam and Yulia Shishkina from St. Petersburg Electrotechnical University in Russia. The short-state path problem is fundamental in graph theory with widespread applications from transportation system to social network and economic modeling. However, existing algorithms like Dijkstra and Bellman-Ford struggle when dealing with large graphs, especially those that contain circles and negative weights. This chart failed with negative X weights. Bellman-Ford handled negative, but its performance decreased heavily on this graph. And our research tackles these challenges by developing a parallel sorted path algorithm optimized for large and complex graphs. Our primary goals are to develop parallel versions of the short-state path algorithm, efficiently handle cycles and negative weights, and leverage multi-core processor to significantly reduce processing time, ensure accuracy and comparative performance of a traditional algorithm. And now several methods have been proposed to improve short-state path computation, like Dijkstra is efficient but limited to non-negative weights. Bellman-Ford supports negative weights but is lower. So recent improvements include Fibonacci helps for Dijkstra, delta stepping, a parallel technique for large-scale graph, and GPU-based algorithm for BFS and SSSP. However, many face issues like loss balancing, graph partitioning, and communication overhead, which our work seeks to address. And our approach builds upon the sequential algorithm developed previously based on adjacency list representation. The core idea is to partition the graph's edge list, assign each part to the processing thread, compute locally, then exchange and makes intermediate result. We implemented the algorithm in C++ using the Boost MPA for processing communication and Boost serialization to handle complex data efficiently. And here is an overview of our algorithm. An initialize sets for past partition adjacency list across trees. Each tree computes different set for source and target vertices. Each train data between trees and calculate intersections and difference then makes update parts and remove invalid X. And the process continues until the starting vertex overlaps with the target, indicating the optimal path is found. Here we demonstrate the algorithm with a simple graph of 8 vertices. Each list processes a portion of the edge list. Through set operation, exchange and merging, the short-state path is constructed in the step-by-step parallel fashion. The final results confirm that our algorithms produce correct outputs in parallel, identical sequential computation. And we ran experiments on Intel Core i7 1200, 12,700, 32 gigabyte RAM, abundant 2022 implemented in C++ with Boost MPA. And we test on synthesis graphs with size ranging from 100 to 100,000 vertices. covering both spreads and distance structures. The algorithm dynamically divides the edge list among trees, performs local computations, synchronizes results, and checks for convergence. The best performance were achieved with 4 threads. Speed up picket that at 4 threads up to 1.5 is faster for 10,000 vertices. And I think more threads actually increase overhead due to synchronization and memory tension. And our findings show that the algorithm scales well up to a point, but like many parallel systems, it faces a performance trade-off beyond the optimal thread count. And we compare our algorithm to Bellman, Ford, and Dijkstra, all using 4 threads on a small graph, 100 vertices. All 3 perform similarly. On large graph, our algorithm consistently outperforms both. Bellman Force is lowest due to OVE complexity. Dijkstra is faster but still lower than our approach on large graph. These results confirm that our algorithm efficiency and robustness. And in conclusion, our parallel sorted path algorithm significantly improve execution time. It handles negative grades, circles, and scales well up to 100,000 vertices. It outperforms traditional methods on large graphs. And moving forward, we aim to enhance synchronization and dynamic trace location, explore GPU or distribute system, improve load balancing for irregular graph, and apply this to real-world problems like smart transportation or social analytics. And this research was funded by the Ministry of Science and Higher Education, project number FSE is 2025-0015. Thank you very much for your attention. If you have any question, so feel free to ask me.
Thank you. Other questions in the audience? Okay, I have a few questions. So my first question is, so you said about negative weights. So can you give some example of a real world problem where this negative weights can be used?
So because of sequencing algorithm are too slow on large graphs, so we decide to run applications in transportation network, or social network analysis, and routing in communication system and biological modeling, where graphs are large and may contain negative weights or circles.
For biological modeling, it's useful. Okay. And the next question is about parallel computing. So did you estimate the scalability of your algorithm? Maybe if you could go back to the plots where you estimate the time, the performance. So you showed 4 threads, right?
Currently, it's optimized for offline computation. So with further improvements in logic balancing and synchronization, it's got support in the range time use, I think.
So I wonder if you use more threads or you even use MPI, so you should be able to use processes in distributed memory systems. So the question is, how large is the communication overhead, and how many threads or how many processes can work efficiently? If you did this kind of research, or if not yet, maybe you plan it for future work.
Here is depends on the size and density of the graph. So we have an experiment with 100,000 vertices and our parallels also takes around 12.5 seconds.
Okay.
Yeah.
That's good. Yeah. Okay. Thank you very much.
Yes.
We have no more questions, I believe. Thank you. Thank you. And this concludes our current session, but we will be back in a couple of hours to continue our section of computational infrastructure, scientific computing infrastructure. Thank you and see you later.
Thank you.
Thank you. Goodbye, everyone.
Thank you.